am going to use delta and sigma. That is, I will write this as delta sigma x delta sigma. Now I compare these two. Coefficient of x delta x sigma, I have here x delta x sigma, x delta x sigma, and compare the two, and that is the condition my lambda has to satisfy. This is the most general condition for a Lorentz transformation. I have only used the fact that this thing is the same in all frames. I have not used anything else besides that. The other thing I have used is a transformation is given. This is the most general case of Lorentz transformation.
It should be eta delta sigma.
Pardon?
It should be eta delta sigma.
Delta. Oh,
In between.
So, any transformation of physical quantity with this lambda satisfying this condition is a 4 vector. Now we are ready to do a little bit more. I purposely introduced the 4 vector here, and I will now go back to standard physics. Then we will come back to the use of 4 vectors. But before I proceed, is there any question on what I have done?
X is a column vector.
Pardon?
X.
X's are all column vectors. Yes.
So when you are taking lambda x,
Then I can treat this as a row vector.
yeah.
If I want to do that, I can. If you think in terms of matrices, I can. Anyway, I have multiplied these two, so there is no. I have not explicitly used the fact that.
But you have flipped that lambda on the right of x delta.
Which one?
Lambda alpha delta. Second length. So
Here,
is it
yes.
lambda inverse?
No, x mu. I am substituting for x mu to be that. That's all.
Yes, sir. But lambda
Alpha delta x delta. That's what I am substituting for. X prime alpha. I had x prime alpha, eta alpha beta, x prime beta. Right? This is what I had. For x prime alpha, I have used that relation alpha delta x delta. Okay?
So these are all matrices.
Yes, they are all matrices.
I mean, how you have flipped the two?
I have not flipped anywhere. I have just kept this relation all the time. I have not tried to keep it on this side. Okay? At no stage I need to write down eta mu mu is only thing I need is eta 0 0 is 1, eta 1 1 is minus 1, eta 2 2 is minus 1. Don't, if you want to think of this matrix, then I will have to write a transpose and so on. I don't want to get into that. Okay. This is the concept of a 4 vector. You will need this concept a little later for understanding various expressions as we will see. The important point is this relation which I have written down. X prime is the linear relation. Any A mu which is A0, A1, A2, A3. Any 4 quantities which transform like this under Lorentz transformation. Of course, this is sum. Remember, Einstein convention was there. I am not using it right now. 3. If this happens, A is a 4 vector. and we will see what is the use of a 4 vector. Notice, if this is a 4 vector, we also have one more comment I would like to make. X prime mu, eta mu nu, x nu is the same in all frames. That is, this is the same as x nu, eta mu nu, x nu. Well, let me write down some O. How was this true? This was true because I made this transformation here. But I am making the same transformation for a nu. So whether I use x nu or a nu, it does not matter. Why? Because x prime nu is related to x nu by this, and a prime nu is related to a nu exactly the same way. So I can write down here mu a prime nu eta mu nu a nu a prime is equal to summation a eta. Just like x prime is invariant, this is invariant. What is the meaning of this? This means a prime 0 squared minus a1 squared minus a2 squared minus a3 squared. Same in both ways. Invariant means same. Same. Let me explicitly write it. I will write this down. This is a very important equation. A prime 0 squared a1 squared a prime 2 squared a prime 3 squared. That's the property of a 4 vector. Now, let me go back to getting relativistic mechanics. The governing principle of getting relativistic mechanics is the following. The main principle is that when velocity becomes very much smaller than that of light, that should go back to the standard Newtonian mechanics. When you have dark velocity, whatever physical law that you write must be valid in all inertial frames. And how do you go from one inertial frame to the other inertial frame? By Lorentz transformation. And what is that Lorentz transformation? I have summarized that Lorentz transformation in just one equation. So, if I make this transformation, then I should be able to see whatever law I write in S should be valid in S1. Now, let me tell you the virtue of writing it in this form. Suppose I write a physical law on which the right hand side or left hand side is a 4 vector. Okay? My law, whatever law I write, I have for my left hand side a 4 vector. And that is related to some other physical quantity, right hand side, which is the 4 vector. And if this is, now I claim, if this is valid in frame S, it will be valid in frame S prime. Why? Because how will this transform? This will transform as lambda mu nu times the 4 vector. And how will that transform on that side? Since it's a 4 vector, it will also transform lambda. These quantities may be very different. This could be force, that could be acceleration. Okay? So, if it works here, it will work here provided I write it in terms of 4 vectors. When I write it in terms of 4 vectors, I get a linear transformation and I will have no difficulty in getting it. So, there are two things which govern relativistic mechanics. One, at low velocities, it better agree with Newton's laws because we know that it works. Second, if it works in one frame, it must be made to work in the other frame. And a very natural way of doing that is write everything in terms of 4 vectors. Because if I write the left hand side to be a 4 vector and right hand side to be a 4 vector, I know for sure it is going to be valid in all frames, if it is valid in one frame. So these are the 2 basic principles of getting to relativistic mechanics. Before I do that, I want to consider the basic idea is try to see conservation of momentum. This will give us a clue on how I will not do it using 4 vectors now. Afterwards, I will start using 4 vectors. Right now, I will just write down conservation of momentum. I will consider the following situation. I will have a ball A. Let me make sure. In my frame S, this ball is moving with the velocity v(i), and in B, another ball B, which is at rest. After collision, this is before collision. After collision, I will write only the velocity v moves with the velocity w. This is my x-axis, and that's my y-axis. Let me go to the frame S prime, in which my ball A is at rest. That is, I am moving with velocity v in that direction. A is at rest, and B moves in the opposite direction with the velocity minus v. Before collision. I am considering absolutely symmetric situation here. So after collision, A will, just like B moved in this direction, this is B, A will move in this direction with minus Wx. Now we are ready to consider the conservation of momentum. Let's see. Initially, there was no x component or no y component of momentum. So finally, there should be no y component of momentum. Now, let me look at the component of A in A. I would like to look at the component of A in S. Shall I do it this way? Yeah. Components of A after collision. Component of velocity of A That's the inverse transformation. I know the components of velocity of A in S prime. I need to find out in S. So what is that transformation? The transformation will be, I just had written it down earlier, it will be Ux will be Ux prime plus V divided by 1 plus V Ux prime by C squared. And Uy would be Uy prime divided by gamma into 1 plus V Ux prime by C squared. These are the inverse transformations. The role of S and S prime have been interchanged, and I would write down those. So, for me, the velocities are given here. So, let's write down W x in A in S frame. These are in the S prime frame. In the S frame would be minus, I have to use this expression, minus Wx plus V divided by 1 minus Wx V by C squared. And Wy S A would be minus Wy divided by gamma times 1 minus Wx C squared. But what is the velocity of B after collision? It is Wx, Wy. So if I assume the momentum along the y, let's look at the momentum along y direction. Let's assume the masses of these are identical particles. That's how I have looked at it. And let's assume the mass of them to be m. M is the mass of this, and m is the mass of that. Then what will happen to the y component of momentum here? The y component of momentum would be m times initially there was no y component of momentum. Yes. Now V develops a y component of momentum. We will write it down as mwy. This is B. What about A? A is minus mwy by gamma into 1 minus wx. Right? This is not 0. So we seem to run into a problem of conservation of momentum if I just use the normal ideas that I had earlier. The solution to the problem is that you assume the masses are also functions of velocity. Later on we will see what is the advantage of doing that in terms of 4 vectors. That's why I have introduced the 4 vectors. We'll come back to it. Right now I am just giving you a physical argument that either you assume masses frame in which conservation of momentum goes away, or you assume masses are given by some functions of velocity. To do that, what I am going to do is I am going to think of a grazing collision. In the grazing collision, what will happen is I will have Wx go to 0. Okay? Then I will get m. If I drop this term, I will get m minus m by gamma. this is hardly moving. So this is at rest. And if it is grazing collision, this has a velocity v. This should be zero. Now, if that happens, then I get m velocity v is given by m rest times gamma, which is m rest divided by 1 square. So, you assume that the moving particle has a mass given by this, then you automatically get conservation of moment. So this is one way of seeing it. There are several ways, and this is one way of seeing the result.
This will happen only when this is what's moving, B is moving along only y-axis, not in x-axis.
I have derived it for this particular case. Actually, it can be done. I shouldn't say derived it. It is if I attribute it this way, then conservation of momentum follows. Okay, it only gives you clue. Later on, we will see how this can be. See, the point is this: you know physics works in a certain region, V less than zero. You want to extend the physics to your lab. There will be several extensions which may match the answer that you get for the Newtonian case. You do not know which is the correct one. The only conditions you know are two. One is it should be valid, Newton's law should be valid when V is very small, and secondly, it must be valid in non-inertial field. So if I write down a law which satisfies this, that's a possible law. Ultimately, the solution lies in experiment. Only experiments can finally decide whether that particular law which you have done extended to a larger domain works or not. Okay, so there are cases in which there are several extensions, and out of that, the correct choice will be determined by experiment.
So here in this case, if you are applying what simple law, if there is collision, will that B will move along x-axis?
No, but what I am saying is, it is a grazing collision. When I am grazing, then nothing happens to this. That's why I am saying Wx goes to 0. Grazing collision means that there is no velocity in that direction. It is just moving like that. This is grazing collision. Okay? Now I am ready to go to the next step. So once I say my mass should be this, how should my momentum be? It should be mass times the velocity. So I will write down my momentum. M0, I will call M0 the rest mass, and square root of 1 minus v squared by c squared times. And I will try my Newton's law, saying this dp by dt. Let me just look at one-dimensional case. So I write down here dp dt of m0 v by 1 minus v squared. So I'm going to multiply this by v on both sides, which is dx dt. No. I multiply this by dv. What should I do? Just a minute. I take dt on that side. Which I can write it as f dx, which is f dx by v. And I bring v on this side, so I get v into d of m0 v. I'll just try to finish this. So I can integrate, which I can write. This is nothing but the work done, change in energy. That's equal to delta E is V times I need to work m0 times dV by 1 minus d squared by c squared to the power half, then minus m0v divided by 1 minus d squared by c squared to the power 3 half times v by c squared. So this whole thing is, one can just add up, one will get 1 squared by c squared. And one can integrate this from e equal to 0 e max e some value, and I will write the final answer. It is m c squared, m0 c squared. Pardon?
So there are two minus signs, one coming from minus half and one coming from the derivative of 1 minus
Oh,
x
yes,
square
this
is
is plus. That is plus. So, when I write out let me briefly discuss this. Notice, this is the energy when I start from V equal to 0 to E. So notice when V equal to 0, I have m0 c squared cancel out. And if V is very much smaller than c, this works out to half m0, which is the standard kinetic energy. Of course, it again required Einstein to realize that the rest energy is m0 c squared, and that in reactions in which the masses can change, that can be converted into different forms of energy. That has been extensively verified in all the nuclear physics as well as particle physics, with all these accelerators which are there with great amount of accuracy. So I think I will stop for today and then continue to work with covalent formation.